250.142 requires a neutral conductor for a grounded system if any of the following conditions exist. Firstly, neutral conductors are used to supply single-phase loads. Secondly, neutral conductors are used to carry unbalanced loads. Thirdly, the system is a grounded Y system. NEC 250.24 requires equipment bonding jumpers to be connected to the equipment grounding conductor, which is typically the neutral conductor in a grounded system. NEC 250.24b requires grounding electrodes to be connected to the equipment grounding conductor, which is also typically the neutral conductor in a grounded system. Therefore, it is generally required to have a neutral conductor in a three-phase panel, regardless of whether the equipment connected to that panel needs it directly for its operation. The reason stems from the critical role the neutral conductor plays in facilitating ground fault current paths, which are essential for the proper operation of overcurrent protection devices like circuit breakers. Even if the equipment itself operates solely on line-to-line voltages within the three-phase system, the presence of a neutral provides a low impedance path for fault currents to return to the source in the event of a ground fault. This low impedance path is crucial because it allows a sufficiently high fault current to flow, enabling the circuit breaker to trip quickly and clear the fault. Without a dedicated neutral conductor, the fault current would have to rely solely on the equipment grounding conductor EG to return to the source. While the EGC does provide a ground fault path, it is primarily intended for safety grounding and may not always provide a low enough impedance path to ensure rapid tripping of the circuit breaker, especially in longer circuit runs. A higher impedance fault path means a lower fault current, and a lower fault current may not be sufficient to trip the breaker within the required timeframe, potentially leading to equipment damage, fire hazards, or even electrical shock. The neutral conductor also serves to mitigate voltage imbalances that can occur in a three-phase system. Even if the connected equipment is perfectly balanced under normal operating conditions, unforeseen events like single-phasing or uneven loading can introduce voltage imbalances. These imbalances can stress the equipment and reduce its lifespan. The neutral conductor helps to stabilize the voltage by providing a return path for any unbalanced currents, thereby minimizing voltage fluctuations. A grounded Y system inherently requires a neutral conductor to function correctly. In a grounded Y system, the center point of the Y-connected transformer or generator is grounded, creating a neutral point. This neutral point provides a stable reference voltage and a return path for unbalanced currents. Without a neutral conductor, the grounded Y system would not be able to maintain a stable voltage and would be prone to voltage fluctuations and equipment damage. Single-phase loads connected to a three-phase panel, such as lighting or receptacles, require a neutral conductor to complete the circuit. In these cases, the neutral conductor provides the return path for the current flowing through the single-phase load. Without a neutral conductor, the single-phase load would not be able to operate. In summary, the requirement for a neutral conductor in a three-phase panel, even when the equipment connected to the panel does not directly require it, is rooted in safety, equipment protection, and system stability. The neutral conductor provides a low impedance path for ground fault currents, helps to mitigate voltage imbalances, and enables the operation of single-phase loads. By adhering to the NEC requirements for neutral conductors, electrical systems can be designed and installed to provide safe and reliable power distribution. Consider the scenario where a piece of three-phase equipment develops a ground fault. A ground fault occurs when a live conductor comes into contact with a grounded surface such as the equipment chassis. In a system with a properly installed neutral conductor, the fault current will flow from the live conductor through the fault path and back to the source via the neutral conductor. This high fault current will quickly trip the circuit breaker, de-energizing the circuit and preventing further damage. However, in a system without a neutral conductor, the fault current would have to rely solely on the equipment grounding conductor to return to the source. The equipment grounding conductor may not provide a low enough impedance path to allow the fault current to reach the level required to quickly trip the circuit breaker. This can result in a prolonged fault condition, leading to equipment damage, fire hazards, or electrical shock. Also consider a three-phase panel supplying a mix of three-phase and single-phase loads. The three-phase loads may not require a neutral conductor for their operation, but the single-phase loads will. Without a neutral conductor, the single-phase loads would not be able to operate. Furthermore, the presence of single-phase loads can create imbalanced currents in the three-phase system. These imbalanced currents can cause voltage imbalances and stress the equipment. The neutral conductor provides a return path for these unbalanced currents, helping to maintain voltage stability and prevent equipment damage. The NEC mandates adherence to prevent potentially hazardous situations. The role of the neutral is multifaceted, ensuring safety, facilitating proper operation of overcurrent protection, and contributing to overall system stability. In the context of industrial or commercial settings, three-phase power distribution is commonplace, powering machinery, HVAC systems, and various other equipment. While some of this equipment may operate solely on the line-to-line voltages of the three-phase system, the electrical panels supplying this equipment often require a neutral conductor for reasons beyond simply providing a return path for load current. Ground fault protection is a critical aspect of electrical safety, and the neutral conductor plays a vital role in ensuring that ground faults are detected and cleared quickly. When a ground fault occurs, such as a phase conductor coming into contact with a grounded metal enclosure, a fault current will flow back to the source. The magnitude of this fault current depends on the impedance of the fault path. A low impedance fault path allows for a high fault current, which is desirable because it enables overcurrent protection devices like circuit breakers to trip quickly, isolating the fault and preventing further damage or injury. The neutral conductor, being grounded at the source, provides a low impedance path for ground fault currents to return to the source. This is particularly important in three-phase systems where the equipment grounding conductor (EG) may not always provide a sufficiently low impedance path, especially in long circuit runs. A higher impedance fault path means a lower fault current, and a lower fault current may not be sufficient to trip the circuit breaker within the required time frame. This can result in a prolonged fault condition, increasing the risk of equipment damage, fire, or electrical shock. The neutral conductor also serves as a voltage reference point in grounded electrical systems. In a three-phase Y system, the neutral point of the transformer or generator is grounded, providing a stable voltage reference for the system. This stable voltage reference is essential for the proper operation of sensitive electronic equipment and for preventing voltage imbalances that can damage equipment. Even in systems where the primary load is three-phase equipment, there may be auxiliary single-phase loads connected to the same panel, such as lighting, control circuits, or convenience outlets. These single-phase loads require a neutral conductor to complete their circuits. Without a neutral conductor, these single-phase loads would not be able to operate. Furthermore, the presence of single-phase loads can create imbalanced currents in the three-phase system. These unbalanced currents can cause voltage imbalances and stress the equipment. The neutral conductor provides a return path for these unbalanced currents, helping to maintain voltage stability and prevent equipment damage. Therefore, even if the primary purpose of a three-phase panel is to supply three-phase equipment that does not require a neutral, the NEC typically requires a neutral conductor to be present for ground fault protection, voltage stabilization, and to accommodate any potential single-phase loads. The specific requirements for neutral conductors in three-phase systems are detailed in NEC Article 250, which covers grounding and bonding. This article specifies the conditions under which a neutral conductor is required and provides guidance on how to properly ground and bond the neutral conductor to ensure effective ground fault protection. NEC 250.24c addresses the grounding of the neutral conductor at the service equipment. It requires that the neutral conductor be grounded at the service equipment to establish a low impedance ground fault path. This grounding connection must be made to a grounding electrode system that meets the requirements of NEC 250.50. NEC 250.28 provides requirements for bonding the neutral conductor to the equipment grounding conductor EG. This bonding connection ensures that any ground fault currents will flow back to the source through both the neutral conductor and the EGC, providing multiple paths for fault current to flow. This redundancy enhances the reliability of the ground fault protection system. NEC 250.30 provides requirements for grounding separately derived systems such as transformers. If a three-phase panel is supplied by a separately derived system, such as a transformer, the neutral conductor of the transformer must be grounded in accordance with the requirements of NEC 250.30. This ensures that the separately derived system has its own dedicated ground fault path. In addition to the specific requirements for grounding and bonding the neutral conductor, the NEC also contains general requirements for the installation of neutral conductors. NEC 310.15 provides requirements for the ampacity of neutral conductors. The ampacity of the neutral conductor must be sufficient to carry the maximum unbalanced current that is likely to flow on the neutral conductor. NEC 314.16 provides requirements for the size of conductor fill-in boxes and conduit. The neutral conductor must be included when calculating the conductor fill-in boxes and conduit. The NEC also requires that neutral conductors be identified by a white or grey color. This color coding helps to ensure that the neutral conductor is properly identified and connected during installation. The requirement for neutral conductor in a three-phase panel, even when the equipment connected to the panel does not directly require it, is a critical aspect of electrical safety and system performance. By adhering to the NEC requirements for neutral conductors, electrical systems can be designed and installed to provide safe, reliable, and efficient power distribution. Furthermore, the presence of a neutral conductor allows for greater flexibility in the design and use of electrical systems. It enables the connection of single-phase loads to three-phase panels, which can be useful in a variety of applications. It also provides a stable voltage reference for sensitive electronic equipment, which can improve the performance and reliability of this equipment. In conclusion, the neutral conductor is an essential component of three-phase electrical systems, and its presence is typically required by the NEC even when the equipment connected to the panel does not directly require it. The neutral conductor provides a low impedance path for ground fault currents, helps to mitigate voltage imbalances, enables the operation of single-phase loads, and provides a stable voltage reference for sensitive electronic equipment. By adhering to the NEC requirements for neutral conductors, electrical systems can be designed and installed to provide safe, reliable, and efficient power distribution. In many industrial applications, variable frequency drives, or VFDs, are used to control the speed of three-phase motors. The VFD can introduce harmonic currents into the electrical system, which can cause voltage distortion and equipment damage. The neutral conductor can help to mitigate the effects of harmonic currents by providing a return path for these currents. In some cases, it may be necessary to install a larger neutral conductor to accommodate the harmonic currents produced by VFD. The NEC provides guidance on how to size neutral conductors for harmonic currents. Also, surge protective devices, SPDs, are often used to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD typically require a connection to the neutral conductor to function properly. The neutral conductor provides a low impedance path for surge currents to flow back to the source, which helps to protect the equipment from damage. The NEC provides requirements for the installation of SPD. Power quality is an important consideration in modern electrical systems. Poor power quality can lead to equipment malfunction, reduced equipment lifespan, and increased energy costs. The neutral conductor plays a role in maintaining power quality by providing a return path for imbalanced currents and harmonic currents. Proper grounding and bonding of the neutral conductor is essential for maintaining good power quality. The NEC provides guidance on how to improve power quality in electrical systems. Electrical safety is paramount, and the neutral conductor plays a crucial role in ensuring electrical safety. The neutral conductor provides a low impedance path for ground fault currents, which helps to protect people from electrical shock. Proper grounding and bonding of the neutral conductor is essential for electrical safety. The NEC provides comprehensive requirements for electrical safety. Periodic inspection and testing of electrical systems is essential for ensuring their continued safety and reliability. The neutral conductor should be inspected and tested as part of routine electrical system maintenance. The NEC provides guidance on how to inspect and test electrical systems. In summary, the requirement for a neutral conductor in a three-phase panel is a multifaceted issue with significant implications for electrical safety, system performance, and power quality. By understanding the reasons behind this requirement and adhering to the NEC guidelines, electrical professionals can ensure that electrical systems are designed and installed to provide safe, reliable, and efficient power distribution. This is especially important in today's increasingly complex and demanding electrical environments.